Typing on his typewriter.
Yeah, that one.
Okay, Devin, if you're looking at this, this was one of the problems we just did. We had to reconcile this. This is about a half a pound per cubic inch of mercury because we took 13.6 times 62.4 because it's 13.6 times the density of water. Divided that by 12 cubed to get this. It's about a half a pound per cubic inch. We did cubic inches because these are measured in inches. And you might want to study that, but this is how you find out the total force on that steel plate submerged in mercury. So I'm going to erase it now. Hopefully when you pause it, you'll be able to study it, because that concept is going to be important for this next part of the lecture. Okay. So what we are considering is on page 421, example 4, the Great Molasses Flood of 1919. 1919, wasn't that near the end of World War I?
Yeah, it was.
More trouble in Boston. Yes.
How different would that be if we did it three-dimensionally instead of just the 2 dimensions?
We're going to kind of do that right now. Now that I think about it, yeah. Maybe you'll be able to see how it would apply, like if we had a hemisphere put in there and how it's poking in on the hemisphere from all around. What's the total force on that? I think we can answer it with this if we went to surface area of the sphere. We'll see. See if you can make what we're about to learn apply to what your questions that's being asked. Okay. All right. So Great Molasses Flood of 1919. Here's the situation. At 1 p.m., right in the middle of the afternoon, well, beginning of the afternoon, on January 15th, 1919, which was an unseasonably warm day. Global warming even then. Okay. I'm not denying global warming, but I'm just saying, we can have warm days and cold days, and they don't belong. Anyway, a 90 feet high, 90 feet high. That is 9 stories. That doesn't even come close. The tower or the round cement thing we used to have on the edge of town. Does anybody remember that?
Yeah.
They dropped that thing. That was 4 stories.
Are you serious?
90 feet high, 9 stories.
Why do they have a 90-foot tall barrel of molasses?
Because it's Boston, they needed
It was right on the train tracks, and that's where they put it so that they could load it into boxcars and ship it around. Okay, now listen up. 90-foot diameter cylinder, metal tank, in which the Puritan Distilling Company stored molasses at the corner of Foster and Commercial Streets in Boston's North End, exploded. That is an overstatement. It did not explode, but it broke at the bottom. It broke at the bottom and just kind of tipped over. All that molasses. That's a lot of molasses. Okay, notice that it's 90 feet tall and 90 feet wide. Big tank. Okay, listen up. Trapping pedestrians. Wait a minute. It says the north end exploded. Molasses flooded the streets 30 feet deep. Can you imagine looking up and seeing a 30-foot wall of molasses rolling at you?
Yeah, we can start.
It trapped pedestrians and horses. In those days, a lot of people had their wagons tied up to the hitching post outside the 5 and dime or whatever. 5 and dime. We used to have 5 and dime. It's like the dollar store. Only things were nickel and 5 cents. Anyway, and this horse is tied up there. He's got a wagon behind a team of horses, and it looks up and goes, "I'm not getting out of this." He's tied there. I'm sure they're scrambling. Rolled over and rolled him into a ball and ran him down the street. Okay. Anyway, knocking down buildings and oozing into homes, it was eventually tracked all over town and even made its way into the suburbs via trolley cars, people's shoes. It took weeks to clean up, I can imagine. You think it's bad when you spill a Sprite on the kitchen floor and it takes you forever to mop it up? That happened this week. I told Alan, don't get that over. It's over within 2 seconds of us. I'm sorry, Tony. All right, let's get some rag. We'll clean it up. Okay, I'll clean it up. All right. So it says, given that the tank was full of molasses weighing 100 pounds per cubic foot, quite a bit more dense than water, we'll go with 100 pounds per cubic foot, What was the total force exerted by the molasses on the bottom of the tank at the time of rupture? On the bottom of the tank. Not meaning pushing outward, I mean weighing down on the bottom of the tank. What are they asking here? Yeah. How much did that molasses weigh? How are we gonna find out? It's not calculus. Weight pushing down on the bottom of the tank.
Figure how much is this?
Yeah. What's the volume of a cylinder? Pi r squared h. This is 90 feet. The distance across is 90, so this is 45, we need r. This is h, that's r. This is feet, so we should be able to figure cubic feet. Volume of that tank is pi, r squared h of any cylindrical tank. This volume is going to be pi times 45 squared times 90.
572,500.
Just give me digits.
572,555.
One more five.
One more five.
So we're talking 572,000. Okay, point.
26611.
Okay, that's good. That's just the volume of it in cubic feet. That's how many cubic feet are in this thing. What did the molasses weigh?
100 pounds per cube.
Pretty easy move, right?
57 million.
So now we've got this and this. That's 57 million pounds on the bottom, sitting on the bottom of the tank. That wasn't calculus. So here's the calculus question. Listen carefully. This will take a little work. What was the total force against the bottom foot-wide band of the tank wall? That's where the pressure was the greatest, is at the bottom of the tank, pushing outward. Weight was pushing down, and it was pushing outward this way, and we want to talk about the bottom foot. This is going to be obviously an over-exaggeration because I want to be able to draw this. We're talking about this bottom part right here, this bottom strip, which is 1 foot. What I want to know is, and using the calculus or whatever that we've got, I want to know what was the outward pressure pushing on the bottom of this tank, the bottom strip.
So
Force, we're talking about force. Now, what was force in the problems we've done today? Force was equal to what? Pressure times area. Area of, okay, let's down. Pressure is what now? If we bust it down? Weight density times depth, which we're calling y. What's the area? Area of what? Area of a strip. How wide is a strip for us?
45. Oh, wait, no, that's, give me 90 feet.
Be wise. 1 foot.
1 foot.
That's what everybody thinks. No, it's dy.
That was my second guess.
Because, listen, because there is more pressure right here on this part of the wall than there is on this part of the wall. So we still have a dy thick strip. This strip, if you will, at this bottom part. I didn't do that very well, but it's supposed to be the same width all the way across. This is still dy thick. The question is, how long is it? So if I draw that strip that I'm talking about, this is dy. What is its length? 90 pi. It's the circumference of the tank. It's wrapped around it. Do you all understand that? See what's going on? Okay. So we now know what the area of the strip is. It's 90 pi dy. How deep is this strip? If this is 0 at the top of the tank where there's 0 pressure and it's 90 feet right down here at the bottom, 90, that's how deep it is right here. How deep is that? Why? That right there is, that's why deep that strip is. So we have our y. We know the density, it's 100 per cubic foot. We have the area of our strip. We just need to collect it with an integral. From where to where?
0 to
89.
89 to 90.
89 to 90. There you go, guys. Very well. Very well done. 89 to 90, because we're at 89 here and 90 here. That takes into account our entire foot wide strip that the integral will collect for us. you see that? Okay, and it's going to be 90 pi dy times this, which is, oh, so that should be 90.
Yes.
90 pi times, which is 100.
Oh.
Do you see that?
Yeah.
So I've taken into account this and this. There's my dy. All I got left is, oh gosh. See, the integral's simple. Once you get it figured out, do that integral. It's huge. Don't forget the 9,000 pi. Remember, when you anti-derive that, that's going to be 1/2 y squared that you're evaluating from 90 to 89.
And this is gonna be.
89 to 90.
89 to 90. Times the 9,000.
253,000.
2,530,000.
What?
2 million. Give me digits.
Oh, yeah.
2 5.
3,0,5,5,2. Point.
Subtract one of those three.
Take one. Subtract one of these threes.
Yeah.
2530552.
Wait, where, what?
Like that.
Yeah.
I got something different.
Kyle,
Kyle, what did you do this?
I don't know. I did from 89 to 90.
What is this? This is force measured in what?
Foot pounds.
You know what? When I told you foot pounds or inch pounds before, I was entirely wrong. Entirely wrong. Force. Work is measured in foot pounds or inch pounds. I was wrong on that, so sorry. Force is measured in just pounds. Pounds of pressure. Pounds of force.
It's 9,000.
So you can imagine why it broke, because folks, this tank, I've read up on this thing. This tank was not designed to put molasses in. It's way too dense. It's way too big. And they didn't build it right to begin with. How should they have built if we were going to draw a cross section of the inside, how should they have built this to sustain this and not break? The sides should have been like that,
Why is that?
because the pressure's greatest at the bottom.
Can they just put more supportive bands on the bottom?
Maybe. Something though has, because this is where the most pressure is, something's got to be done to either build it properly from the inside like this, possibly like that.
So just making the shape different helps with.
Yeah, because a dam is built like this, as we saw before. The dam is built out like this with the water behind it here.
Yeah, so could you bend it outside too? It doesn't matter which way you bend the bottoms.
Yeah, as long as you made it thicker. Yep. Yep. You could put bands on it,
Okay.
as long as your rivets. That's where your weakest point would be. Your rivets or your welding. I'll make sure that holds up really well too. Anyway, something had to be done, and that thing was just a straight walled tank, and so it busted on the bottom. It split. You could hear it ripping. I read that. You could hear it ripping from a long ways. And it just ripped. It kind of tipped over as it started oozing out. It just kind of tipped over on the side, and all that molasses went on. Crazy.
Where's the 100 come from again that we times?
It's the density of molasses.
Oh, right, yeah.
It's the density. That's this part of it right here is the density of the substance.
And we didn't convert that. Okay, that makes sense.
Okay, now we're going to do something entirely different. Still has to do with calculus, because it's still area under a curve, but it's a complete switch of gears. It's called normal probabilities that you see there on page 422 in the middle. Okay? Normal probabilities mean it belongs to a normal curve, and a normal curve, a lot of people call it a bell curve. You've heard that, have you? Okay. I'm going to erase this so that Devin can participate. I just looked at that. It looks like a belly button. That piece of the wine that I didn't. Well, what are you doing drawing bellies, Miss Jay? Are you crazy? All right. Okay, so this curve that we're talking about, in a general way, it's on the x-axis, it's on a number line anyway, and we draw it like this, and it goes up, and it comes back down, and it's supposed to be symmetric, and I try to do my best, but it's never quite right. But we're going with it. Okay, this right here, this line right smack in the middle, it splits it right in half, it's supposed to be symmetric. That is the mean. and we call it, or we symbolize it with a Greek letter M. We pronounce that mu, like mew, like the sound a kitty makes, mew. That's a mu. And the reason that, look, it looks like a U with an extra tail on it. It's an M that's been squeezed together. It used to be like this. That looks like an M, kind of, right? Squeeze the thing together, you get mu. That's supposed to be an M. It's Greek letter, okay? Greek letter mu stands for mean because it starts with M. Okay. Then if you go out certain distances on this thing, if you go out here, this is called 1 standard deviation. And you're going, how do you know how far a standard deviation is? Well, a standard deviation is far enough out both sides of the mean so that the space from 1 standard deviation right and left is always 68%. We call this a standard deviation. And again, we use small Greek letters. This is you can often see it written like this, an SD, or the Greek letter for it looks like that. It's a small s. Capital S, as you know, looks like that. Small s looks like this. Okay? It's a small sigma. Stands for standard deviation. So this is sigma 1. This is sigma -1. If you draw another one, the exact same width out here, right there, like this, and pretend it's the same width, this would be sigma 2, and this would be sigma -2. And that from here, well, it's kind of hard to do. From here to here is 95% of the data. So strung across here like that whole thing, I don't know, from here to, I guess I'll put a little arrow right here, going in like this, to there. That whole thing right there is 75% of the data, 95. So within 2 standard deviations, you expect to find 95% of the data. That's what they'll say. If you draw 3 standard deviations out like this, by the way, the ends of these are asymptotic, so they never do touch the x-axis. But by the time you get out 3 standard deviations, within 3 standard deviations, negative or positive, this distance from here to here, oh boy, I'm really running into trouble here. This distance right here is 99.7% of the data within 3 standard deviations.
Are the standard deviations all an equal amount apart?
They're all, yes, this distance from here to here is the same as from here to here is the same as from here to here on a normal curve. The first 2 standard deviations are away from the mean enough so that there is 68% of the data. Okay, now if you'll take a look at page 423 and the column, the middle picture in the column shows you those 68, 95, 99.7. Okay, now, oh, by the way, they say -3 sigma. Sorry, I've got this. I haven't done stats in a long time. It's still the same notion. It's just now a coefficient. This is, no, that isn't. That's 1, this is 2, this is 3, this is -1, -2, -3. Standard deviations. Okay. This became something that most people were aware of because most people were parents when this became something that was talked about with measuring IQ. You know? Measuring people's IQ, and they tried to design the test so that the scores on them, if you got 100, a score of 100 was the mean, and the standard deviation was 10 points in either direction. That's very difficult to write a test that'll happen that way. It's much easier to just write a test and then force it into these types of numbers. Anyway, what's really weird is before political correctness came along, and I probably shouldn't bring up these words, but I'm going to because we're so politically correct these days. This distance from here to here, if you were within 1 standard deviation on your IQ score, that is from a 90 to 110, you are considered normal. You're a normal person, normal intelligence. From here to here, so you're going from from 80 to 90, that would be your score that you got on your IQ test. You were called a moron. From here to here, that would be from 70 to 80. You got a score on your IQ test. You were an imbecile.
Is this like actual terms?
Yes, yes, this was in psychology books.
That would be so embarrassing.
Yeah, it's because we've become so politically correct. It didn't have the same horrible, meaningless, or awful connotation. Anybody to the left of that, 70 and below, was an idiot.
So it's
nicer
nicer
to call.
Yeah. From here to here on the top side, if you scored between 110 and 120, you were called bright.
I like how it's like more.
From here to here, you were considered gifted. We still use these because they have positive connotations. And beyond that, guess what? And you can see that the tails of this have to split the remaining 0.3%. There were not very many idiots. There were also not very many geniuses. There weren't really very many imbeciles or gifted people. Okay? There were a few more morons and bright people, but I mean, those spaces are bigger. That's just to give you an idea where these things became popular. And I want you to, people became aware of them. They didn't remember the 10 standard deviations and how things work statistically. They just remember these names. Okay, if you will look at the bottom picture on 423, it shows you that normal curves, it depends on the spread of the data. Normal curves can be really tall and narrow, or they can be all really, really flat like the blue one. It depends on how spread out the data is. Nevertheless, no matter which of those three curves are the extremes that you see there, one standard deviation from the mean in any of those curves, and on the black one you can see one standard deviation would be very small distance out, but it will contain 68% of the data. Are you with me?
All right.
All right. So turn the page. Oh, by the way, the function that is the function which makes this curve is 1 over the standard deviation times the square root of 2 pi, all times e to the negative x value, wherever you are on the x-axis, minus mu squared divided by 2 sigma squared, or to the standard deviation squared. And you would find the area under the curve depending on where the person was or and you would find the probability of landing in a certain space.
And
Good
that's
question. I didn't memorize that.
No, your calculator has it memorized. Thank you, TI programmers. TI programmers are awesome.
They do have.
You will also probably not be looking at the actual curves, but you will be using a distribution which understands these. You do the calculations. There's a normal PDF and a normal CDF. Normal refers to the shape of this curve. You want to use CDF. It stands for calculating the density function. PDF stands for probability density function, and it's the graph of it, and I've never found much use for it. This is enough graphing to get you an idea what's going on. All right, take a look at example 6, please, before we actually go to the calculator, so turn your calculators off for a minute. Example 6 says, suppose the telephone helpline takes a mean of 2 minutes to answer their calls. If the standard deviation is half a minute, then 68% of the calls are answered in a range between 1.5 and 2.5 minutes. Does this make sense to you? Yeah, you follow that? Okay. And 99.7% of the calls are answered in a range between half a minute and 3.5 minutes. So you stand a pretty darn good chance you're going to be answered before 3.5 minutes is up. But it may take up to a half a minute for them to even pick up and say, can you please hold? Now we're talking about spinach boxes. I know you guys probably don't do a lot of your family's grocery shopping, or maybe you do, I don't know, but there is a frozen food section, and there are frozen vegetables like peas and corn and edamame and stuff like that. They also have, or used to, and maybe they still do, they have, my mom used to bring them home with peas and corn stuff, and it was like a family serving. It was in a box about this big and about an inch tall, and it was jam-packed full of vegetables, like spinach. Okay, frozen box, about like this, almost square, about that tall. Mom used to stack them up in the fridge, or in the freezer. We didn't have spinach very often. She didn't think spinach, thank goodness. She didn't like it. But there was peas and corn all over the place in these little boxes. You just pull one out, toss it in the pot, and that would be the family serving for them. Right. Okay, says, suppose that the frozen spinach boxes marked as 10 ounces of spinach have a mean weight of 10.3. What? Says 10 ounces on the box. Why would the average weight be 10.3?
Package more for your money.
The way
You would get more than it says for your money.
Because it's the box weight.
Why isn't the mean weight 10? Because what?
The packaging.
No, we're talking about 10.3 ounces of spinach. The guy who's doing the packaging put 10.3 in for his mean on purpose. Because if he didn't, folks, exactly half the stuff coming off of the assembly line would be underweight. Somebody would catch him if only half of them were less than it said on the package and half were more. Somebody would catch that. 50% underweight, under what you say is in there can be damaging to your business because it looks like they're ripping you off. But if only a few percentages of them are under 10, first of all, your chances of getting caught at it are not that much. And you can prove to people only 7% or whatever are underweight. And if you get an underweight one and you want me to give you an overweight one, I'll do it, kind of thing. But you don't want to do half and half. Way too much of a chance of getting caught getting an inferior product. It's better to put a little bit more in each one and sacrifice that than getting sued or getting a bad reputation. You understand what I'm saying? He did that 10.3 on purpose. And with quality control in the factory, he has standard deviation down and have his normal curve of weights be fairly narrow. His standard deviation is 0.2 ounces. So even right here, he's still overweight by an ounce, right? Even right here, he's only underweight by 1/10 of an ounce. Somewhere in here, right in here, is exactly where 10 ounces is. You with me or not?
I'm with you to the end.
To the end, yes. Okay. All right. So the A part says, knowing we've got a mean of 10.3 and a standard deviation of 0.2, it says, what percentage of all such spinach boxes can be expected to weigh between 10 and 11 ounces? Now we need this guy. Between 10 and 11 ounces will be somewhere right in here was where 10 is. This is 10.3. 11's way the heck up here somewhere. Because we're only going by 0.2, 0.2, 0.2, 0.2 up until we get to 11. So it's way up here. So we're talking about basically how much area is under this curve from about right here up to 11. Here's what you do with your calculator. You go find the button that says distribution. It's above, it's the blue aspect of your VARS key. You see it? DISTR.
I see it.
It's right here above the VARS key, right there. See it? The blue distribution. Okay, good. All right. When you pull that up, you go second and that button, you get this, you should. For those of you watching, it's a lot of glare. And we want to choose normal CDF because we want to calculate something. So we go to normal CDF and hit enter. Pulls that up on your home screen, and this is the syntax. By the way, I might have my, does yours look like that? Normal CDF parentheses?
No, mine.
No, mine has lower upper.
Okay, but does anybody look like this at all? Anyone say normal CDF parentheses? Anybody? Well, then maybe I better change my, road. I don't know what happened, but anyway, you need to give it 4 pieces of information. If you have it like mine, which apparently none of you do, you have to put in the, I can't remember, where's my syntax? There it is. You have to put your upper bound, your lower bound and your upper bound, which in our case would be 10 and 11, right? So I'm putting 10, 11. And then mu, which is 10.3, comma, for me anyway, it's a comma, and sigma, which is 0.2. That's the syntax. So, can I see yours?
Oh, now it gives us that.
I got it.
Mu is the.
So this is probably what yours looks like, Devin, maybe. If it's like that, then you put those numbers in that we're talking about right there. And if it looks like mine, when you do it, you put it in like that. So it'll say normal CDF, it'll come up and give you a parenthesis, and you've got to put the upper, lower, mu, and sigma with commas in between. Okay? All right. Okay, so if you hit enter at that point or paste, you should get 0.933. Yeah? Okay. So 0.933 means that 93, a little more than 93% of the stuff coming off the assembly line will be between 10 and 11 ounces. And it virtually means, like I told you, if we started out here with this is 10 and we're only going up by 0.2, we're clear up here. So we're into the 0.3% tail up here. So virtually what we're saying is that about 7%, a little less than 7% coming off the line will be underweight, under 10 ounces. Okay? You understand how to operate that? That's just the A part. You ready to move on?
Yep.
Stay with me. It says, what percentage would we expect to weigh less than 10?
About 6.7%.
I agree. We can get that from this, but to actually calculate that, if you didn't have this already, you would go grab your distribution, go to normal CDF, and this time put your lower bound at something like negative 0.99999. I mean, way the heck down now on the tail. Way the heck left. If you want to know up to something, then you let your lower bound be really, really small. Like negative 5.9. Right? That's really out of control there. And then your upper bound would be 10. And then mu is the same. And you're right, you get about 0.668. 6.68% come off underweight. That can be dealt with if the public has, if there's an outcry for underweight spinach boxes. You can have them. Okay. C part says, what's the probability that the box weighs exactly 10 ounces? And the answer is 0.
Exactly 10 ounces.
Because what you're looking for here, like for example, if you're looking for, if 10 occurs right here on the number line, and we did that problem, the B part, we were looking for the area under this curve, which was only 6.6%. What we're looking for here, if you want to think calculusly, is we're integrating from 10 to 10 of the function, the normal function. But we all know that I don't care what the function is, it's 0. And you're going, but can't the box weigh exactly 10 ounces? No, you cannot.
Why not?
If you had a scale that was sophisticated enough that you could take it out as many zeros as you want, you would eventually get a number.
Would you?
10, you would.
Well, what if it was like perfect?
Exactly.
Nothing on this earth is perfect. You learned that in seminary.
No.
Everything
This
is
box
corrupt.
perfect.
There is a 10 on the number line, but there is no spinach box that weighs 10. There's also no spinach box that weighs 10.1. Exactly.
In that case, there's no spinach anywhere.
That's what it seems like, but that's not the math behind it. The math is, it's the probability of that happening, weighing exactly 10 is 0.
Well, I know the math says that, but my logic says there can't be.
Logic's wrong.
Okay, well, you go ahead and let that logic roll around in your skull, but the math is what you're doing in
It'll be
here.
a couple items.
You can't integrate from something to the same something and get any area at all. There is no probability that that can happen.
Is that because all of them are gonna be irrational?
What's that?
Are all of the boxes gonna weigh an irrational number?
Nope, they can be
No,
rational.
this is a
The
control.
probability of finding them is 0.
I see. So it can.
Whether it's that irrational or rational, the probability of pulling one off the line. The weight is exactly 10. Now, if you say 10 ounces to 100, you can get those all day long. You know, pull those out. It's exactly 10 ounces. You can 10 ounces to an infinite number of accuracy places. You're always going to hit something that's a little more or a little less than 10 out there somewhere.
Spaces in theoretical physics, you can't
That's the
Oh, my hand.
Okay, folks, we're at the end of this section. We're at the end of sections in this book. You learned your last section in this book. Doesn't mean you learned your last concept. Not by a long shot. But we are done here, and we need to prepare. After you've done this, we need to start preparing for your second quiz and your test over this chapter, and then we will start hitting other concepts that are not in this book that you need to prepare for the final. And then we're going to practice. Okay. So there you go. I will send you those other things as they come along, Devin. See you later.